Okay, so yeah, so I'm going to give a run through of a typical kind of data science challenge we face here at the trade desk. I will give a bit of a run through of what it is we do. I mean, I think James summarised it quite nicely, but yep, we're not a finance company, not a trading company. So I'll give a bit of a run through of that, namely programmatic buying. I'll then dive specifically into what we do within, what we're trying to do within supply path optimization and what exactly that means, before getting, I guess, into the sort of the meaty data science of it, which is the interesting stuff and how we can leverage data science to come up with a solution to the problem. Okay, so programmatic buying, what exactly does that mean? So this is a very simple view of the digital advertising ecosystem. In reality, it's actually a far more complex web, but I think conceptually like this is fine for now. So if we go from the left to the right, we've got consumers. Consumers are you, me, practically anyone with eyes on a screen. And whenever we visit sites, we stream content off platforms, that gives opportunity for an ad to be placed in front of us. Now, when that opportunity comes along, publishers that typically will represent these sites, platforms, will send out notification that there's opportunity for an ad to be placed. So they'll send out this notification, which we call an available bid request, or just to abbreviate that throughout this presentation, I will call it an avail. So when I say an avail, that's what I mean. I mean that signal being sent out into the ecosystem saying that there's opportunity for an ad. So that gets sent out to supply side platforms or SSPs. They also sit on the sell side of the equation. And their primary objective, I guess, is ultimately to obtain as high a price as possible for that ad. So then they can go out and try and, yeah, as I say, garner as high a price as possible. And here's where the key interplay comes in. So SSPs will then send out that avail to the buy side, namely DSPs, demand side platforms. These represent advertising agencies who represent the brands that we all know and love. Now, it's here where the trade desk sits. So the trade desk is a DSP, one of the biggest DSPs operating, and our business is buying up these avails. So SSPs send over opportunities for us to buy. We, amongst other SSPs, will potentially reply with a bid if we deem it valuable, or one of our clients deems it valuable for one of their advertising campaigns. Okay, so as I said, that's a sort of very simplified version of what actually goes on. This takes a step down complexity lane, I guess. Still quite simplified, but I think it works okay. So what publishers actually tend to do is they'll generally send out the avail to more than one SSP, with the view that the more SSPs they send it out to, the higher chance they have of obtaining a high price. So in this example here, publisher sends out the avail to two SSPs, SSP 1 and 2. They will then hold an auction. This will be with a bunch of participants, the demand-side platforms or DSPs. In this example, the trade desk is participating in both auctions here. So there's 3 participants, trade desk participating in each. And as you can see, so trade desk wins on both. We value the avail the highest, £12, £10 respectively. Now, we've won those auctions. This is first price auction into the price. The highest price bid is the one that gets carried all the way back through. Those prices, the SSP will then pass back to the publisher, who will hold, in effect, an auction of auctions. And then the highest overall price from that gets the gig. And the ad associated to that bid will be placed. And then, in this case, we get billed £12. Now, again, that is still a slight simplification of what happens. So SSPs are also in the business of making money. And the way they make their money is they take a fee of the bid that's passed on. So in this example here, SSP1 has a fee of 25%, SSP2 has a fee of 15%. So these fees are deducted from our initial bid, and then they'll pass on the remainder. So in that case, we have from our bid through SSP1 a bid of £9, and then SSP2 £8.50. Now this sort of begins to lean into what supply path optimization is looking at. Because ideally, in a functional marketplace, we would want to reward SSPs that are offering the lowest fees, and that's all how we would expect a functional marketplace to work. However, this isn't the case here. The SSP with the higher take rate, SSP1, has actually ended up getting the gig, which isn't ideal. And I should probably also add here that you may be thinking, why are we bidding different amounts on what is actually the same piece of inventory? That's because the SSPs may alter, or certain fields might not come through certain SSPs. So the contextual data that comes along with the inventory, whether it be like the site it's being held on, maybe information about the user, the location, some things don't filter through, and that can lead to discrepancies in pricing across SSPs. Okay, so as I say, that sort of then leads nicely into supply path optimization, and here's basically the setup for the problem. So publisher sends out the avail to multiple SSPs. The SSP then passes the avail on to us. Now, we've got a choice here. There's a bunch of different paths that we can actually potentially bid on. Now, we don't know how many paths in a live setting we're actually going to see. We just treat these independently as they come through. But this is what's happening in reality, and offline we can assign avails back to a common auction so we can see this play out. And the question is then, which of the paths is optimal for us to buy through? So there's a sort of an additional reason to it just being the optimal path, in that each path has a sort of computational cost associated to it when we process it. So even though there's only one ad opportunity, there may be any number of avails that we have to process. Now, each of these we process through our internal auctioning logic, where all of our clients can value them and then potentially bid on them. And there's, as I say, a cost associated to doing that. However, there's only ultimately one ad slot available. So, and that's not ideal for us. When you scale this up to billions of auctions a day, then that can become expensive. So we want to limit it for reason one, that being the reason. And then how can we do that? So if we consider, again, in the live setting, we don't know how many paths we're going to receive. Publisher sends through avail to SSP. SSP passes it to us at the trade desk. Ideally, what we'd like is some model which interprets that avail as it comes in. So it gives us some kind of indicator as to whether it's the best path, and then that can inform a decision whether we drop that avail at the front door or we then go on to process it through our internal auctioning logic. Okay, so we've established that we want to whittle the number of paths down. Then it's a case of, well, what do we whittle it down to? So there's a whole bunch of different dimensions that we might want to choose on, but for the purpose of just this presentation, we'll just focus in on the monetary aspect, and that being that we want to maximize the percentage of our spend that reaches the publisher from our initial bid. Namely, we want to minimize the take rate. We want to try and select the SSP with the lowest take rate across this selection of paths. And so just to reiterate that, so going back to the example I gave earlier, this would not be a good outcome for SPO, because here we're selecting and we're buying the avail through an SSP with a higher take rate than what else is available. Hopefully all making sense so far. Okay, and so just to narrow down that workflow then, so it's not just a predictive model we're looking for here, it's actually a take rate predictive model where we can look at the contextual data of one avail coming in, try and determine the take rate associated to that avail, and then either drop or process accordingly. Okay, so diving a little bit more into take rates and then how we can sort of harness this from a data science perspective. So similar setup here again, we've got our two auctions. In this instance, however, the bids are slightly different. We bid £11 through one and £10 through another. Take rate's still exactly the same, 25% and 15% across the two SSPs. And that leads us into this scenario here. So this is a little bit peculiar in that because of the take rates, we've actually ended up winning with a lower bid. So we've bid twice for the same piece of inventory, the same avail, but we've actually ended up winning with our second highest bid, which is a bit counterintuitive. Now, for us, we don't know what the take rates are, right? We don't know what they are, nor do we know what the publisher receives. This is pretty much all we see. We see we've bid £10, we've bid £11, and we've ended up winning with £10. So we think this can tell us something about our take rates here, R1 and R2. And we call this an example of losing to a lower bid. Okay, so what exactly is losing to a lower bid? So as I say, an instance where we've won not through our highest amount, and that can actually tell us something about the lower bound of the take rate of SSP1. So I've just worked the equation up there. It's just 1 minus the winning bid divided by the losing bid. So we know in our example here, the take rate of SSP1 is at least 9%. So that begins to give us a little bit of information as to what the take rate might be. And then we can do this across a whole bunch of different loss to lower bid scenarios. And then I'll come back to this a little bit later, but this is just another way of conceptualizing exactly the same thing. So our winning bid there on the right, where we bid at £10, and then on the left, our losing bid, we know that the fee, or we assume that therefore the fee, the take rate for SSP1 must be at least that difference, which as a percentage again works out to 9%. Okay, so I'll now try and walk us through how we can actually leverage this to try and set up a machine learning model to predict take rate. Okay, so the setup is exactly what I've just described, in that each row of our training set you can attach to one loss to lower bid scenario. So as I say, in the live setting, we can't work. We don't know how many paths we're gonna get through for a given bit of inventory, but we can do this offline. So offline we can assign avails to a common auction, and then from that we can work out where we see this loss to lower bid happening. And so what we have here is sort of two identical streams of data attached. So on the left side we've got all the contextual data that the winning bid sent through, and the SSP associated with that. And then joined, we've got the loss to lower bid contextual data that the SSP sent through, along with the take rate lower bound, which again, as I explained, can be calculated using that equation. Okay, so in an ideal scenario, all the information we receive on either side would be the same. So in this example here, we know that the site of the ad placement is New York Times, the location of the user is the US, it's an image, so it's a static ad, and it's going to be shown on an Apple device. That's fine, all good. But as I said, given that we often see differences in the fields that get sent through, hence that discrepancy in price. In that example I gave, the £12, £10, or £11 and £10. So as I say, we get these discrepancies, and maybe there's no particular comment on these SSPs. I'm not pointing fingers, but for the SSP on the losing side here, for some reason the country of the user hasn't come through, and also there's differences in the device type. So this is a really common scenario, and we need a solution which is sort of robust to this. Okay, and then just to put a point on the put a full stop on it. We have billions of rows of this. So although instances of loss to lower bid is kind of rare, I think it happens approximately 2% of all bids we send out. We hold billions of auctions, so we still have a lot of this data to lean on and leverage. Okay, so the way we try and then leverage this is, if we consider that we have our predictive model as a sort of black box object, let's say, we create two carbon copies of it. So it's exactly the same model. If we just say, just for argument's sake, it's a neural network, so the weights are exactly the same within that model. It's exactly the same architecture. It's just two carbon copies of exactly the same thing. We can then pass the exact same feature set into both instances on the model on either side of that loser-winner equation. And so just again to say, this is actually two carbon copies of the same model. It's exactly the same. In reality, we end up only having one model. The weights, so the loss gradient associated to each weight can just be summed across to the two instances, and then the weights updated accordingly. So these two models can then try and predict the take rate. We can try and predict the take rate of the winning SSP. We can try and predict the take rate of the losing SSP, that which lost to a lower bid. Now, we could just leave it there, and we could just try and have a model which predicted that, but that doesn't allow us to sort of bake in some of the assumptions we have around the auction logic. And so to do that, we have then both of those values getting passed into a custom kind of likelihood function, which I'll try and walk you guys through now as to what that actually looks like, along with the take rate lower bound value. So there's three components going into this likelihood function. It's the winning SSP's take rate, the losing SSP's take rate, and that likelihood function, and the take rate lower bound into that likelihood function. Okay, so what does that actually look like? Okay, so I'll try and build this from the ground up. Feel free, if anyone has any questions as I'm walking through this, just shout them out, because I can appreciate this might get a bit confusing, I'm not sure. So we have our losing SSP's take rate on the x-axis, the likelihood on the right. the first element of this setup is we take our take rate lower bound, which we've calculated with that equation, and we set that as our absolute minimum for the losing SSP's take rate, right? We're saying that it makes no sense that the losing SSP's take rate can be less than this, given what we assume to be true about take rates. And so based off that, what we say is that we assume the losing SSP's take rate is likely to be closer to that lower bound rather than further away. And this is a consideration of the competitive pressures that are probably there in the industry. If we have an SSP that's constantly being insanely greedy with their take rates, we assume that they probably just aren't in business. And so there is that sort of competitive pressure. So we assume that the losing SSP take rate is likelier here as opposed to here. Hopefully all good so far. As I said, we assume that the only reason why loss to lower bid instances occur is because of differences in take rate. There could be network issues or other things, but we assume that this is the sole reason for that, and hence the losing SSP's take rate must be greater than that take rate lower bound. So going back to that example, the lowest value it could be was 9%, but in reality it was actually 25%. It's somewhere greater than that. However, we still fit a curve to this region between 0 and 100% of the prediction, primarily for the early stages of training a model, when it may start spitting out predictions that make no sense, and we need to try and tell the model somehow, no, you actually need to push your predictions up on that losing SSP side. So we do have a curve there, even though in reality we think it's sort of, nonsensical that any of the actual predictions could be there. Okay, hopefully still all good. So I showed this slide just now. This is, again, our take rate lower bound value, but we can actually go a step further than that. So what we can say is, given that we have our model one, or on the losing side predicting the loser's take rate, but then also the winning side predicting the winner's take rate. So we can say, we know for sure that the minimum SSP1 fee is this take rate lower bound. It is actually the take rate lower bound plus whatever the winner's take rate is predicted to be. So if the model predicts that the winner's take rate is 10%, that would therefore push down further what the losers could be, and then the actual bid that ends up the publisher seeing is actually somewhere in this shaded region here. Okay, so to bake that assumption in, we then shift our lower bound along, so from take rate lower bound to take rate lower bound plus the winner's take rate. Again, both outputs, well, the winner's take rate is output of the model, both are components going into the likelihood function along with the loser's take rate. So here now we sort of have the entire setup for what the likelihood function looks like. So we have all three components, the take rate lower bound, the winner's take rate, and the losing take rate. Okay, but there's more. So given what I've said so far, either of these scenarios would be perfectly legitimate. So for example, the model could predict a take rate of 80% for the winning SSP and a take rate of 90% for the losing SSP. And given the constraints I've said so far, that would be perfectly reasonable. However, given this notion of sort of industry pressures, not only within an auction, but also industry-wide, we expect that take rates as a general are likelier to be lower rather than higher within the industry. And therefore, we suspect that this case is more likely than the case on the right. And so in order that, so yeah, just have that as the assumption there. We assume take rates generally are lower rather than high. And so to bake that assumption into the model, we have the likelihood function, which I just explained, and then take the product of that with a second likelihood function, which looks at the loser's take rate exclusively and just says, okay, we assume that that should be nearer 0 than 100. And that's how we constrain in that way. And that's the setup for the likelihood function. And then from there, we can just take the negative log of that, and then that can be trained as you would train any sort of standard model, with the benefit now that the single model has sort of implicitly learned to push take rates up in winning cases and push them down in winning cases and up in instances of loss to lower bid. So this model can then just be plugged straight back into that workflow I explained earlier, and then we can inform whether we should drop or keep an avail based on take rate. Yeah, I've included some pros and cons of that. So that likelihood function allows us to bake in a lot of, as I say, assumptions around the intuition behind the auctions. The model can be immediately lifted out of there and pointed at a single avail to predict take rate just using the contextual data of one avail. However, there are some limitations, particularly with how the training set is set up. So SSPs that have the advantage of potentially being a monopoly may not really succumb to those competitive pressures, don't really care about them, which sort of throws all of the assumptions around minimizing take rates out the window. And then also the training set is kind of biased on inventory, which is commonly seen in loss to lower bid scenarios. And a good example of that is if a particular SSP has exclusive access to some kind of inventory, that will never be seen in the training set. And therefore, how do we hope that the model sort of generalizes to that? We hope it generalizes well, but it's a risk. So,
you asking a question? Oh,
yes. Yeah, so that was all I had. Sorry.
What happens if the take rates are dynamic?
Sorry.
What happens if the take rates are dynamic?
If the take rates are damning? Dynamic. So we would hope that the neural network of the model can tease out the underlying pattern of the take rate from that contextual data. So we assume that it's not fixed fee, but given the features that we can ingest, that the take rate will be consistent if we saw exactly the same set of features again, if that makes sense.
But our take rate, can the take rate be dynamically speaking? So if you
Our take rates obviously depending on something unless it's a particular, particular audience, a particular geography or whatever. There's one dynamic it could be. And then they might just take rate based on how much they think it's worth.
Oh, so you're asking, is the take rate determined sort of after the bid price is received?
As part of the bid, if I'm sending an ad, I'm new to something like that.
Yep.
I've got an audience, and I don't really want to exist. And they've got to deal with the SSP to say, you know what, if we've got this kind of audience, we'll reduce your take rate, we'll build a new type, and we want the bids.
Yep.
And then give a lower take rate.
Yep.
So how do you then got to be able to say,
Yeah.
billions of bids.
Yeah.
Therefore, how does it work out?
Yeah.
Take rate ranges to decide whether you
Sure. So in that case, so let's say, we've got an SSP and then for a particular subset of inventory, they're reducing their take rate. How that could potentially manifest itself is that they would then flip the side of the equation they're on in that loss to lower bid scenario. So perhaps they end up not losing so many, we don't end up not being on the losing side of loss to lower bid scenario so much. Perhaps they're more on the winning side. And then that push down from being more on the winning side would hopefully sort of trickle through into the predictive performance of the model. Have you got a follow-up?
I'm just trying to figure out, I'm trying to understand what you're saying, because obviously the world is moving really quickly, as you said.
Yeah.
There's a lot of competition around SSPs wanting to bid and take bids.
Yeah.
So you've got and they're all potentially different, having different take rates with each of the publishers. So the take rates may not be the same across.
Yeah, of course, yeah.
And they may have different deals for different inventory. There's a whole bunch of there's a whole bunch of dynamics there, right? There's a whole bunch of dynamics. So what I'm trying to figure out is how do you work that out for the best deal for the customer, right? The customer is the agency, or it's the brand of the agency.
So the focus of this model here is solely to try and infer take rate. We're not passing any sort of judgment on what might be good for our clients. This is solely a mechanism to potentially drop avails at the front door based on if we think the take rate is too high.
Right.
Because as a general, we want to try and incentivize SSPs to push their take rates down, and that allows more of our spend to make its way through to the publisher, which are the sort of content creator in the space.
Right.
Does that answer your question?
Yeah. I mean, I'm sure there's a longer discussion, but I get
Sure,
I get
we
it.
can speak after if you like.
And
For sure.
I'm just trying to understand just how the markets work. How the SSPs actually function across all of the publishers, and whether they are quite dynamic. Because you're competing, you're bidding.
Yeah.
So are they smart on their side, knowing that you guys are trying to work out take rates on the other side, right? So
Well, you'd hope so. You'd hope so. We can discuss more after for sure. You had a question?
Publishers game their data all the time.
Yep.
So how do you account and what steps do you take to account for that?
Well, obviously, so this model can only do the best it can with the features that we're able to ingest when an avail comes in. So we get a set of fields that come in along with an avail, like I described, that contextual data. And we have to do our best to try and tease out a pattern from that. So obviously...
Filters to combat your filters. That's the whole, most of such big sites, they have filters to make sure that their data is what you see. And they're gaming that all the time.
The publishers? Yeah, and so again, so there's a couple of different things there. We can only see this signal in instances of, again, we need these to pass through as instances of loss to lower bid. And then we try and retrain the model as frequently as possible. So if there are changes in that dynamic, then we can pick them up as quickly as possible. Does that answer your question? Okay.
Assuming that you guys have done multiple reiterations of the model that predicts and drops the higher take rates, I'm curious, are there any, because I'm assuming there's sorry, should I repeat this again? Yeah.
I can hear you.
Yeah, okay. So assuming that you've done this for a certain period of time, what are some other factors or ways that you're looking? Because my assumption is that there's a curve, right, that you've reached to an extent that you can, I don't know, improve the prediction model, right, 80% or 90%, whatever the proprietary number might be. So so I was saying that I'm assuming that you've predict this prediction model. Can you guys hear me?
Sorry about that, Mike.
Just my question is that I'm assuming that there's a prediction model that you guys have for base, and there's a certain after certain iterations, it has come to a certain point in terms of prediction, right? 85% or 95%. And this, I'm assuming that there is a reach curve that you might reach or you might have already reached in terms of training the model. I'm curious, what are some next ways that you're looking at for certain factors, I don't know, tweaking hyperparameters,
Sure.
or a new approach that you're looking at to improve the model?
Sure, yeah. So this model is kind of tricky in the sense that we don't have access to any ground truth at scale. We don't know what the take rates are. So one way we can do this is we just look at the business sort of performance metrics using the model. So if our average spend per ad goes down, then we see it as sort of taking us in the right direction. As for ways we can sort of improve this further, as I say, the SPO project as a whole could potentially consider a whole bunch of different dimensions as to whether something should or shouldn't be dropped. So here, just focused on the monetary element of it, but there's other things as well, such as that manipulation of fields, which I showed. We want to try and penalize SSPs that are doing that or gaming the system, as you said. And so there are other sort of elements to what SPO could look at to sort of give a more holistic view of what we deem optimal.
Just a quick question. I don't want to keep going over the... Sorry. Just another quick question. I don't want to go over the dynamism of the take rate too much, but is there a temporal component here? So if a bid is not filled, you're basically dropping the price or dropping the take rate. Does that happen?
So if a bid, so are you saying if a bid for some reason isn't filled, let's say, just for some context here, so let's say the SSP has passed through a bid with a floor price. Let's say the minimum must be this, and therefore no one bids on it. Is your question then, will they then drop that next time that similar ad becomes available?
Yeah, they take out their margin.
Yeah, absolutely. That potentially could be the case. Again, this model's signal is this loss to lower bid scenario. So we're only really leveraging the data when we know we've bid twice on a common item and we've won with the lower bid. It doesn't really, and if scenarios like you described fall into that, then we can leverage that. But that is definitely a sort of limitation of the model in that its scope is exclusively this loss to lower bid scenario. Yeah.
2 more questions?
Sure, yeah, absolutely.
So, where would you like to go?
Gentleman there, had his hand up.
Sheng, good choice. Thank you.
Hello. My question is related to how dynamic, basically a follow-up question on whether or not the take rate could be dynamic. Because I've worked in the buy side in the past where I had to buy leads through lead generators. And in that case, I still need to predict what other players in the field might do with the lead. Because sometimes when the lead comes through, they come out at the price, say £12, and then nobody wants to buy it and the price drops. So I don't know if this type of mechanism does happen in SSP side where they might come out with a take rate of 25%.
Yeah,
and then people are playing, oh, they're not buying my lead because they infer that my take rate is really high, and then they start dropping, and how does the model then react to that?
Maybe this is, maybe just to comment on this sort of like the dynamism within the take rates. We don't consider the inventory over time. So we're not sort of keeping track of the inventory and seeing the floor price was here, now it was there. Obviously we have that data, but that's not a consideration within this model. It's only individual instances and whether they fall again into this loss to lower bid scenario. In that case, they'll be seen. But then at least in this project, there's no comment on price fluctuations over time for a given bit of inventory. I mean, obviously, you can then take that. It's how granular you take that, right? You could say, is it the same bit of inventory when the same user's looking at it, when the same user's looking at it on a phone, or blah, blah, blah. So you see what I mean? Yeah.
This is a quite stupid question because I'm not from the programmatic buy industry. Can you just flip back to the two machine learning model, that slide?
Will that do?
Yes. Or the next slide, or the likelihood function, yeah. Yep, this one maybe. Yep. So just want to make sure I understand the whole thing. So we are on the right-hand side, we are using the context of the loss to lower bid contextual data.
Yep.
And then the label is the take rate lower bound.
So that it's not really the label. We're not actually training on the take rate lower bound. It's just a component. It's a component going into the likelihood function. So we have these three components: the winning take rate, the losing take rate, the take rate lower bound, all go into this likelihood function, which is then trying to maximize the likelihood of the predictions of the model given the data.
Yep, and then we use the same likelihood function and a trained model to predict or to do the inference for the winning bids. So we can infer the take rate for the winning bids. Is that what the whole process is?
So the sort of outcome of this is a model that can just predict take rate given a single set of contextual data. But we want the model to learn and leverage this dynamic between losing bids and lower bids. So theoretically, you know, if cases where Casale or Pubmatic show up more in the winning side, then the model may learn that their bids, their take rates are generally lower because they tend to be more often seen on the winning side of the equation in this loss to lower bid scenario. So this is a sort of way of implicitly telling the model, steering the model in that direction.
Okay. And the second question is about the likelihood function, because I see the likelihood function, the maximum likelihood point is actually the take rate lower bound. So does that mean that when we are going to do the inference on the winning bid data, actually we're also predicting the lower bound of the take rate because that's the maximum likelihood of the function.
So again, what this this curve is trying to enforce into the model is that take rates between the winner and the loser are likely to be closer together rather than further apart because of industry competitive pressures. It wouldn't make much sense in general if the losing SSP's take rate was always way up here and they were just far too greedy, because then they would likely just be out of business. So yeah, does that answer your question?
Yeah, so does that mean that when we are doing the prediction, basically the maximum likelihood part is always the take rate lower bound? So that's my question. Yes, the likelihood factor.
Yeah, so the likeliest scenario here is that the winning and losing SSP take rates are incrementally close to each other, right? And then as the further away they get apart, we say we think that's a less and less likely scenario.
Amazing. Zach,
cool.
Can we have a round of applause, please?
Cheers. Cool. Cheers, Matt.